Hey friends, it's good to be back with you. Today it's time to get into infinite series. What the heck's an infinite series? Well, it's about what it sounds like. An infinite series is a sequence of algebraic terms that goes on forever. One term is added to another, and another, and another, and another, and another, and it never stops. Now, infinite series sounds pretty abstract, and I suppose it is in one sense, but it turns out to be extremely practical, and it's something you use all the time, perhaps without knowing it. Now, the idea of an infinite series is very old. First example I know of is a guy named Zeno of Elea, who was a Greek philosopher and posed what we now call Zeno's paradoxes. He proposed some thought experiments that seemed to be mathematical paradoxes. And here's one that's pretty well known. Let's say I want to travel some distance from point A to point B. Now, Zeno suggested you could do this in a very particular way. Let's say I'm trying to go from there, almost, to there. All right? Well, we'll do this in a specific way. We'll start by moving half the distance. So I'll start here, there, and I'll take a step that's half the distance. And then the next step will be half the remaining distance. And the next step will be half the remaining distance. And so on, and so on, and so on. He observed that this looks like 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. And because this term, 1/2 to the n, never goes to 0, you'll never actually get there. All right? Now, at the time, this was indeed a paradox. Now that we know what calculus is and we know how to handle infinite series, it's not a paradox. And here's why. Let me show you the solution to this one. What he said was, equivalent in modern mathematical notation, is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/2 to the n. And he's right. That never goes to 0. Does it converge? Now, what does convergence mean? It means that no matter how many terms you add up, you're eventually going to get some fixed finite value, so that an infinite number of terms can converge to a finite value. That's a big, big idea. Now, poor Zeno had no idea that was possible. That realization happened much, much, much later. So it's no longer a paradox, although it is kind of an interesting head scratcher for when you're new to math. Well, how do you turn this? How do I find S? Because I can't keep adding terms and adding terms and adding terms. It will look like it's converging, but I haven't proved it's converged. Well, let's do this. Now, did I think to do this? I did not. I looked this up. And this is the solution. Let's just multiply S by 2. 1/2 plus 1/8 plus, oops, I missed a quarter. There we go. Quarter plus 1/8 plus 1/16 plus da-da-da. Okay, there it is. Wait a minute. That is S, isn't it? That's this. Well, let's see. That means 2S equals 1 plus S. And that means S equals 1. So, an infinite series can converge to a finite value. Now, this method only works with this series. It's the nature of proofs. They don't tend to be general. This is one of those times. So this is a simple example of how an infinite number of terms can be added to come up with a finite value. So it isn't really a paradox, but at the time it seemed like it. So you're probably not going to use this particular series very often. There are other series that you will use pretty regularly. Probably the most widely known of them is the Taylor series. And here's what it looks like. Okay, that's the Taylor series. Now let's pause for a moment and make sure we understand the big idea here. The big idea is that I have some function, f of x, and I'm going to approximate it with all this stuff. And that 3 dots means it goes on forever. Now, if I actually go on forever, that really is an equal sign. If I take those 3 dots away, it's not an equal sign. Now it's approximately equals. Well, I obviously can't write down an infinite number of terms. No matter how many I write down, there's always one more. So this is always an approximation. So a couple of points here. A is some number, okay? A is a number, and we know what it is. All right? And so what we're doing is we're saying we're going to expand f about a. What does that mean? It means we're going to anchor this approximation about this number a, so that it's more, the approximation is more accurate close to a than it is anywhere else. All right? And you just pick this number. You can pick anything you want as long as you can evaluate it. Now, the little prime symbols there indicate differentiation. So there's the first derivative, the second derivative, the third derivative, and there'll be a fourth derivative and a fifth derivative, and so on. So it's important that f of x be infinitely differentiable. What's that mean? Well, about what do you think? It means you can take as many derivatives as you want. Well, let's try this. What if f of x equals sine x? Is that infinitely differentiable? Yes, it is. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. What's the derivative of negative cosine? Sine. And so on. This goes on forever. Right? So that's infinitely differentiable. Is this infinitely differentiable? No. What's the first derivative? 2x plus 3. What's the second derivative? 2. What's the third derivative? There isn't one. Okay? So this is not infinitely differentiable. Okay? We need an infinitely differentiable function in order for this to work. Fortunately, there's lots and lots of them out there that are, including sines and cosines, which you see a lot. E to the x is another one you see a lot. Okay, so what would this look like? Well, let's try f of x equals sine x and a equals pi. That means this approximation is going to be pretty good near pi, near x equal pi. So let's see, what's f of a? Well, that's going to be sine of pi. Okay, that's easy. What's the derivative of sine? Cosine. Cosine of pi. And remember, this right here, this right here, this right here, those are numbers. And we know what they are. We have to know what they are. So we know what a is, and we know what the nth derivative of a is. That's a number. That's not a function. What goes in the parentheses, that's a function. So I'm going to write x minus pi, and that's 1 factorial. That exclamation point means factorial. So the factorial of a number, like the factorial of 3, is 3 times 2 times 1. The factorial of 4 is 4 times 3 times 2 times 1, and so on. Factorials get big really fast. So you can see by the time you get out to 4 or 5 factorial, these additional terms are tiny, tiny, tiny. I have to say, when I was little, and first time I came across this, I had no idea what it was. I was a kid. And I know it's hard to believe, but there was no internet back then, so there's no way I could find out. Didn't occur to me to ask anybody. And so I didn't know what that was. Like, how do you read that? I know how to read 1, 2, 3, 4. Well, how do you read that? Well, little me went, that's 2. Well, turns out that's not right, but it seemed like it at the time. So let's see, derivative of cosine is negative sine pi. I guess I should be consistent here, shouldn't I? X minus pi squared over 2. I'll get rid of that. And so on. Now, what's going on here? That's a number. That's a number. That's a function. But if you look at this, there's an x, there's going to be an x squared and an x there. There's going to be an x cubed and x fourth. What I'm doing, what Taylor series really does, is it takes an infinitely differentiable function like sines or cosines and approximates it with a polynomial. Well, why would we want to do that? There's a couple reasons. One is that pushing sines and cosines around in equations gets cumbersome very, very quickly. Pushing polynomials around, that's a lot easier. There's another one that's even more subtle, but perhaps more important. Think about how you calculate sines and cosines. Say you pull out your calculator. Say you pull out your handy-dandy, trusty TI-30, the world's most perfect calculator. Costs like $5 and you can't kill it. And it probably costs more than that now, but you still can't kill it. When you press the sine button and you get a number, what is it doing in there? Well, it's a circuit in there, isn't it? In fact, specifically, it's a digital circuit. Well, digital circuits only get to add, subtract, multiply, and divide. That's what they do. Well, how do I get that out of a digital circuit? This is add, subtract, multiply, and divide. That's what's going on the right hand of the equal sign. Now, is it exactly this inside the calculator? Probably not. There are more sophisticated series approximations, but conceptually it's pretty close to this. We'll check it out here in a few minutes on my computer, and I'll show you how this works. So how many terms do you need here? I don't know. How many decimals do you want on your screen? I haven't counted the decimals on a calculator screen in a while, but the last time I did it, I think there was 13 digits across the screen. So how many terms do you need out here to get to 13 digits? Well, some, but not very many. Now, there's one variation on the Taylor series expansion. And what I'm going to do here, let me erase, let's see. I'm going to erase this for a second. There's one specific example. What if A equals 0? What you get then is called a Maclaurin series. You get a Maclaurin series. And Maclaurin series are even easier. So what's a Maclaurin series look like? Well, this is still true, except A is 0. And x minus a, that's just x. Because these are so easy to work with, when you ask for a series expansion in MathCAD or MATLAB or whatever your favorite number crunching program is, unless you specify x as something other, a as something other than 0, you're going to get a Maclaurin series. And these are super easy to write down. And in the right circumstances, they can be dang handy. So with that, let's go to my computer and let's see some examples in MATLAB.